My name is Yanyan. I come from Nanjing University. Today I will present our preliminary empirical study, changes in C++ to Rust, translation with larger language models. The power and the challenges of C++ is obvious. C++ is a powerful programming language, excels in system programming such as operating system development and game development, such as game engines, and it also excels in embedded systems such as microcontrollers, IoT devices. However, the inherent challenges of C++ is also obvious. Its complexity and memory unsafe makes it difficult to use the next time. When we develop a larger project, and we found that while the C++ is powerful, the OOP and the templates can introduce intricate dependencies and complex error handling. And the manual memory management also is error prone, such as use after free. Non-point dereference. And now Rust is into the picture. We found that Rust is memory safety without performance compromise, as it is zero-cost abstraction. And Rust can guarantee the memory safety using the ownership and lifetime checking. Thus, we have a lot of research working on the C++ to Rust ecosystem, such as interoperability and code translation. This is the most common two approaches, such as interoperability, such as we use CXS generate function and type declaration for Rust and C++. And we use these declarations, we can operate C++ and Rust code in each other. BindGen also generates foreign function interface binding for Rust to access C or C++ libraries, limited to handle, but it's limited to handle complex features, such as we can't handle the Rust, the C++ OOP features. CBindGen generates C or C++ handler header files for Rust libraries. That is, we can call the Rust library or Rust create in the C++ code. The next approach is the code translation. However, existing research has focused on the C to Rust translation. The scarce C++ to Rust translation, the representative work is the C Rust, but he only translates a subset C++ subcode, such as ironclad, into Rust with manual effort. Yes, we know we use the manual effort. Hey, it's not mine. It's not in my computer. Thank you. Some research purposes source-to-source compiler to translate a subset of C++ to Rust, and some researchers utilize LMs to translate the C algorithm related C++ code to Rust code. And in this work, we want to systematically evaluate the effectiveness of the state-of-the-art LMs to translate the complex C++ code to Rust, focusing especially on the code translation instead of the interoperability. And our translation granularity is also small. We choose a small but complete translation unit, such as a class or other unit like a function. Then we use a granular translation unit can break down the large and complex C++ code into a small but complete code snip, and our LMs can read this the small but complete counter-translator unit into the promote and translate them. Another concern is that when we input a long C++ code to the LM, it might be introduced the model holifications. And our research question focuses on two research questions. The first is the correctness. We need to know when we use LM to translate C++ code to Rust code, and the syntax and the semantic correctness of the translated Rust code. The next is we want to analyze the root cause. When we translate the C++ code to Rust code, it may be uncompilable. Yes, it may be introduced syntax errors and or semantic errors. Yes, they can't generate the same output. Thus, our study framework consists of three key elements. The first is the feature decomposition. Yes, we break down the whole C++ code into a series of dependent translator units, such as a function, and then we introduce dependencies analysis and extract the dependent global symbols, such as we use another function in this function. Yes, we call the function, and this function is dependent another like classes and all other structures. Yes, when we translate this function, we need to tell the LM which the dependent class or structure what the definition is. Then we follow the feature translation and the syntax checking. Then the final is the semantic checking. We need to ensure that the C++ code and the Rust code can generate the same output when we introduce the same input. Next, we have in detail steps of the first is the C++ feature decomposition. Yes, we use passing clone to extract to pass the whole C++ code, and we extract the C independent translator unit, and in this step we fill out external or standard libraries, such as we use external library, but we can't know the source code or the interface of this code. In this scenarios, so we need to fill out these external libraries. Then we extract C++ features like classes, templates. The next step is the dependency analysis and the translation ordering. We need to conduct dependency analysis and order the translation unit. Yes, we need to translate the first the independent C++ feature, and then after translate these features, then we can translate other. The other is also depend on the formal global symbols. As for each C++ features, we can extract a variety of the metadata, like the classes. We need to extract its name, its hierarchy, inherent hierarchy, and its member, and its member function. After we extract the features, and we need to translate them one by one and syntax checking them. Thus, we first to load the C++ features and provide a comprehensive context to the LM, such as the feature definition. This is the code snip, and the dependencies is the amount of dependent global symbols, and the translation rules. We construct a structured translator promote such as the translation instruction and the libraries and the dependent global symbols and the feature definitions and some examples. Yes, we need to tell the LM how to translate the C++ macro to Rust macro is the code examples. After translate each translation unit, we need to apply a syntax checking layer. We employ the Rust C to check the Rust code and to check whether it's syntax correct. After it's syntax correct, we need to add the dependent symbols. We combine them into one independent Rust file and check the dependent symbols are correct. As for the semantic checking, we need to load the input and output of the C++ code, and we also build an execution driver for the Rust code and use the same input and to check the output of the C++ and the Rust code. As for our setup, we select the dataset and our metrics and our models. As for the dataset, we use the row set code and CodeNet. This is a comprehensive dataset covering diverse programming tasks. As for the metrics, we use the two metrics. The first is the syntactic correctness. Yes, we need to know how much the ratios of the proportion, the ratios of the syntactically correct Rust features compared to the original C++ features. As for the semantic correctness, we need to know the proportion of the Rust files producing output consistent with the original C++ code. As for the model, we use the general LM. The first is the GPT-4 Turbo. The next is the DeepSeek V3. They have a strong code understanding capability. As for the first RQ, we focus on the correctness. We evaluate the model performance. We can see that the GPT-4 Turbo excels in class translation in the CodeNet dataset. And for the DeepSeek V3, it shows the competitive performance in macro translation and template improvements. However, these two models have a common weakness. They struggle with Yanyan as global translations. We have two key findings. The first is the significant performance variability, as we have different performance in different C++ features, such as we can translate 100% accuracy on simple features like enumerations and class features as the CodeNet dataset. The major challenges is also lies in the complex features like classes and templates. And the model difference is the GPT-4 Turbo outperforms in class translation. Meanwhile, DeepSeek V3 shows strength in function handling. The second finding is the feature-specific translation difficulties. We can find that the LMs can well handle the struct enumeration, but they have difficulty in translating templates, units, and global variables. Also, we can find that the two models perform well in the CodeNet dataset. So we also have a dataset dependency. The next is the root cause analysis. In this IQ, we have a separate result of the GPT-4 Turbo and the DeepSeek V3. For the GPT-4 Turbo, we have many syntax errors, as we total have 45 syntax errors. We found that the method of function call is the highest proportion of the errors, as they may call the non-existence method. This is because of the differences of the C++ and the Rust features. The next is the macro or variable translation. This is efficient attention to Rust specific requirements. They have a wrong translation of C++ code to Rust code. As for the semantic errors, the I/O consistent issues is the most issues. We have found that when we have the same input, the output is different from the between the C++ code and the Rust code. As for the DeepSeek v3, we also have some syntax errors translated, but it's different from the GPT-4 Turbo. As we can see, the template parameter constraints and the ownership models is the most occurred. And the scoop implementation errors is also the main causes. And the semantic errors of the DeepSeek v3 is also same with the GPT-4 Turbo. However, the DeepSeek v3 has fewer method call errors, as only have one method call errors. The finding of the root cause analysis is also have the two main findings as the template and the macro translation barriers. We found that we also have some gap to translate the C++ template or macro unit to Rust compilable Rust code. And the next is the feature-specific translation difficulty. We have the memory manager gap and other method mapping errors. Our summary is, and the future work focus on the drum challenge is the syntax errors. We need to, the first thing we need to do is fix the syntax errors. Yes, we have we need to some efforts to fix the syntax error to improve the syntactically correct Rust code. The next is the feature performance variance. We have found that we have high accuracy on basic features, but significant drops with the complex constructs such as units, templates, and global variables. As for the semantic consistency, we have fewer semantic errors compared to the syntactic errors. And our future direction is focused on the developing comprehensive translation framework for larger scale C++ code project. And we need to also focus on the object-oriented features to Rust paradigm conversion techniques. Thank you.